Hi, Mrs. Bricky here. This is section 3.5 on the graphs of rational functions. There are three topics in this section, all related to graphs of rationals. So when we're graphing rational functions, we are always having to focus on some of their key features to help us graph them. They're pretty complicated graphs. I have a couple little examples over here on the side of what they might look like, and this shouldn't be your first rodeo with these, so hopefully you are kind of familiar with what kind of shapes might come up and what these types of functions look like. In order to find the key features of a rational function, the first thing you need to do is have that function in factored form. You may have like a GCF you need to factor out. You may need to factor a quadratic. It shouldn't get into higher powers than quadratic though. So when you look at a rational function, you might notice that it has vertical asymptotes. Those are caused by the fact that we can't divide by 0. It can have multiple vertical asymptotes like this one at the bottom, or it might have a single vertical asymptote. It is also possible that a rational function won't have a vertical asymptote, but those vertical asymptotes come from the denominator, and they come from the fact that we can't divide by 0. You might also have a factor that cancels out, and if some factor cancels out, like if you had a factor that is the same on the top and the bottom and it cancels out, that can cause a hole in the graph. You can't really see these holes in the graph if you look at it on technology or something, but they might exist where the function is undefined for that particular x value. So we'll find the vertical asymptotes from the denominator. We can also find the x-intercepts of the graph by setting the numerator equal to 0. So they often have an x-intercept. It's possible for them to have more than one x-intercept. It's also possible that they won't have an x-intercept. But x-intercept will come from the numerator. Y-intercept we can find the same way we find for any function by substituting in 0 for x. The y-intercept, again, is where it crosses the y-axis. And then the horizontal asymptote, probably the most challenging to find for these types of functions. We find that horizontal asymptote by comparing the degree in the numerator and the denominator. So I have a couple examples of different horizontal asymptotes that we can look at and talk about. But again, you want to look at those polynomials on the top and the bottom, and you want to focus on the powers that you see. So if the power in the numerator is less than the denominator, then it's going to have an asymptote at y equals 0. If they're the same, then we have to look at the ratio of those two leading coefficients, a over b. And if it is a higher power on top, there is no horizontal asymptote. It's a slant or oblique asymptote, and we won't have to graph any of those types this year. So here are three examples of rational functions that have an asymptote at y equals 0. So you can see that in all of these functions, we have a power that is higher in the denominator. So we have x equals, or x with power 1 in the denominator here, so we have that asymptote at 0. Here we have an x with the power 1 on top and an x with the power 2 on the bottom. And since that higher power is in the denominator, that gives us that asymptote at 0. And on this one, we have power 3 on the bottom and power 1 on top. So again, we get that asymptote at 0. So if the higher degree is in the denominator, you are going to have an asymptote at y equals 0. If you have two powers that are the same, then you need to focus on their leading coefficients. So we have 3 over 1 here for our asymptote, so it's y equals 3. We have 8x over 2x. They have the same power, that is a power 1. So that's an asymptote at 4 if we reduce that 8 over 2. And watch for negatives. This one has a coefficient of -9. Our x is a power 2. On the bottom, we also have power 2 with a coefficient of 2. -9/2 is -4.5. So that was just a couple examples of different horizontal asymptotes. So the first topic that you'll have is that you want to be able to find the asymptotes of a rational function. You won't have to graph the function itself, just the asymptotes in this topic. So to find the vertical asymptote, we'll start with that one. The vertical asymptote runs up and down. So the vertical asymptote comes from our denominator, and we set that denominator equal to 0 because we need to figure out what value of x is going to cause division by 0, and for that x value, this function will be undefined. So if we solve for x, we get x equals 7/2. If you're plotting these on a coordinate plane, which you'll have to, sometimes it's good to get the decimal equivalent of that. So 7/2 is 3.5. So we would place our vertical asymptote at 3.5. And in ALEKS, placing these asymptotes is very easy. All right, and then once we have that horizontal asymptote placed on our graph, we want to place once we have the vertical one placed, we'll want to place the horizontal one. Horizontal one we get from comparing the degrees. So in our function, we have a degree 1 polynomial on top and a degree 1 polynomial on the bottom. That means our powers are the same. So we're going to look at that ratio of leading coefficients. So our horizontal asymptote is going to be y is equal to -12 over 2, which reduces to -6. And so we would place that horizontal asymptote at -6. And that's all you would have to do for this topic, is place those two asymptotes on the coordinate plane. The next topic is going to be to graph rational functions. So you'll start exactly like that last topic by placing your horizontal and vertical asymptotes, but then we'll have to plot a few points to get the graph to sketch. So starting with the vertical asymptote happens because we cannot divide by 0. So we set our denominator equal to 0. I would add x to the other side of the equation to get 2 equals x, and that is our vertical asymptote. For the horizontal asymptote, I need to compare degrees. And when we compare the degrees, we can see that they are both degree 1. This is a degree 1 and a degree 1. Since those degrees are the same, we want to do the ratio of the leading coefficients. Watch out for cases like this where you have a coefficient of -1. So I wrote 4. So 4 over -1 is equal to -4. So we would plot that other asymptote at -4. Okay, and then we have to plot 2 points on each side of the vertical asymptote. So what I would do is look at the location of that vertical asymptote at x equals 2. And so we're going to sub in 2 x values on the left-hand side and 2 x values on the right-hand side. So for this function, I think I would start with 0 and then sub in 1. And then jumping to the other side of the asymptote, I would sub in 3 and 4. So subbing in 0, I get 4 times 0 minus 6 over -0 plus 2. That's -3. So I can plot the point 0, -3. If I sub in 1, I get 4 times 1 minus 6 over -1 plus 2. and that is negative 2 over 1, so negative 2. When I sub in 1, I get negative 2. Okay, and I need to have 2 points on each side of that vertical asymptote. So I have 2 points on the left, and now I need to sub in x equals 3 to get a couple points on the right. 4 times 3 minus 6 over negative 3 plus 2. That's 6 over negative 1, which is negative 6. So that's the point 3, negative 6. And then finally, sub in 4. Now I don't have to pick the values right next to the asymptote. I could have picked another value as well. If your point that you end up with has a fraction as its y value, there is an option to plot those sorts of points. 10 over negative 2 is negative 5. You'll probably notice some symmetry. See how it's kind of rotationally symmetric there? Once you have 2 points on each branch plotted, then you can just click on the graph icon and Alex will draw those branches through the points like this. Okay. The final topic is a matching topic where we have to look at 2 equations, which I have on the right there, and we have 6 choices of graphs that we need to try to match them to. So in order to match these, I would use their asymptotes, use their y-intercept, and even if the y-intercept isn't helpful, you can use any point on the graph as well. So the first thing you probably want to do to help you match these is to factor them. So the denominator of this function is going to factor as x minus 2 and x plus 1. So we would look for, on the graph, vertical asymptotes at x equals 2 and negative 1. So let's see, 2 and negative 1. Graph A does not have asymptotes at 2 and negative 1, nor does graph B. Okay, so graph C is possible. Graph D is not. Graph E does have vertical asymptote at negative 1 and positive 2, and so does graph F. So when you look at your first characteristic, you'll probably still have like 2 or 3 possibilities. If we look at the horizontal asymptote, the top is degree 0. There's no x on top, and the bottom is degree 2 for this function. So the horizontal asymptote is at y equals 0. So that can help us eliminate graph C, because we should see the asymptote down here, and graph C does not have that. Now, both graph E and graph F do have a horizontal asymptote at y equals 0. So we can eliminate C, and so now we know that it's graph E or graph F. And then I'm going to look at those 2 graphs for a second and see if I can see something that sort of sets them apart from each other. And what I notice is that graph E has a y-intercept at negative, 3.5, and graph F has a y-intercept at 0. So I can use that y-intercept to help me finish up. For this function, f of 0 is 7 over 0 squared minus 0 minus 2. That's negative 7/2, which is negative 3.5. So it looks like this one has the correct y-intercept for my function. So I would choose graph E. Okay, let's try to match graph H. So again, I would start with factoring. So this is 2x over x plus 3 times x minus 3. So it looks like our choices are going to be A, B, or D. Those are the ones that have those vertical asymptotes at +3 and -3. Okay, so let's look at our horizontal asymptote next. I guess I should write down that those were our vertical asymptotes. Okay, so the horizontal asymptote, if we compare the degrees of this function, again, this is degree 1 if it's just an x. So this is a higher power in the denominator. So our horizontal asymptote is y equals 0. Now, unfortunately, the horizontal asymptote did not help us eliminate any. So we're still left with the choice of A, B, or D. Let's look at the y-intercept. For these functions, a and b both have a y-intercept of 0. D has a y-intercept near to -1. So let's see what our y-intercept is here. If we sub in 0 for x, we get 2 times 0 over 0 squared minus 9, and that is 0. So we can eliminate graph D, because graph D has a y-intercept around -1. So we've eliminated D and it's A or B, but none of the things we've checked so far have helped us. So I would look for something on a place on the graph where you see different behavior on the two functions. So you could check maybe sub in 4. So I can see that for x equals 4, graph B is above the x-axis, is a positive number close to 1, and for graph A, it's a negative number. So just find a spot where the two functions are different and evaluate the function for that number. So I'm going to sub in 4. This would be 2 times 4 over 4 squared minus 9. That's 8 over 16 minus 9 is 7. So it looks like it's a positive number, a little bit above 1. And so that fits with this one because on graph A, it should be a negative number. So that means we have graph B here. Sometimes matching these can be a little tricky. Just do your best and, check all of your attributes, and always, if you're stuck, you can always try evaluating and just matching it to points on the graph. So let me know if you have any questions on this topic. Thanks so much.